Welcome back. In this fourth segment, we will look at more examples of proofs of big O relationships. In our first example, we will prove that f of x, defined as 999 times x squared, is big O of x cubed. So remember what that means is we need to find an x cubed upper bound for this expression. The general approach we've been using so far successfully was to pick an x that is large enough, in other words, to pick a k that allows us to prove an x cubed upper bound for this term, and then we'll be getting the value for c almost immediately that will form a good pair of witnesses for this relationship. So let's assume that x is large enough, and in particular, let's assume that x is strictly greater than 999. So as a result, x is strictly positive, and therefore x squared is also strictly positive. Therefore, we can multiply each term of this inequality by the constant x squared. Since it's strictly positive, it will not change the inequality. So when we do that, we get the new inequality 999 times x squared is strictly less than x cubed. We're almost done since this is f of x. This is a constant times x cubed. All we need is the equal sign on the inequality, which we can add as an inference step, as we've been doing all along. So in conclusion, we just prove that if x is large enough, then f of x is less than a constant times x cubed. So here is the formal definition of the big O relationship. In this case, k is equal to 999, and c is inferred automatically from this inequality. In this case, c is equal to 1. And this concludes our proof. Now remember that there are many possible pairs of witnesses for the same big O relationship. So to illustrate this point again, we're going to prove the same big O relationship using a different pair of witnesses. So this time we're going to assume that x is strictly greater than 1. So what can we infer from that? Well, therefore x is strictly positive, and again x squared is also strictly positive. As a result, we can multiply each side of this inequality by the same number, namely x squared, without changing the inequality. And when we do that, we get x squared is less than x cubed. Since 999 is a positive number, we can multiply both sides of this inequality by 999 to get this new inequality. And as always, we can infer the less than or equal corresponding inequality. And we're done. Notice this is f of x. This is a constant times x cubed. So we prove that if x is large enough, namely greater than 1, then f of x is upper bounded by a constant times x cubed. So here is the definition of the big O relationship. In this case, k is equal to 1, and c is obtained or read out automatically from this step. It's the constant in front of the x cubed, and that's 999. So in conclusion, we have a second different proof of the same big O relationship. Notice in this case, k was really large and c was much smaller. In the second proof, k is smaller and c is really large. And you could use other values of k and c to prove the same big O relationship. Now, for our third example, let's use the same f function that we used in the two previous examples, but this time we're going to prove that it's big O of x to the fourth power. Now, as it turns out, we can start the proof exactly as we did in this case. I'm going to copy this line as is, and remember what it said is that if x is greater than this number, then f of x is less than or equal to x cubed. Now, we don't need an x cubed upper bound, we need this upper bound. But that's pretty easy to obtain because x being greater than this number is greater than 1. And if x is greater than 1, then x to the 4th power is greater than or equal to x cubed. So we can infer that right away, and now we're done. We have f of x here. We have a constant times x to the 4th power here. In other words, if x is large enough, where k is equal to 999, then f of x is upper bounded by c times x to the 4th power, where c is equal to 1. And therefore, we match the definition of the big O relationship with the following witnesses. So, this completes the proof. I want to make a small comment here. We actually didn't really need to write this proof because we know, and that's the advantage of using the reference functions, that x to the 4th power, when x is positive, grows faster than x to the 3rd power. So as a result, if f of x is big O of x cubed, in other words, if it's upper bounded by x cubed, then clearly it's going to be upper bounded by a function like x to the 4th power that grows faster than x cubed. So almost automatically we have a proof that f of x is also big O of x to the 4th power. And of course it's also going to be big O of x to the 5th power. And big O of x to any power that's greater than or equal to 3. So to summarize, we proved in two different ways that f of x is big O of x cubed, and then we proved that f of x is big O of x to the 4th power and any larger power of x. But actually, remember, f of x for us is the runtime of some algorithm. And we want to prove that the runtime is as small as possible. In other words, it doesn't grow any faster than a given function. And so we don't want to increase the power of x, we want to decrease the power of x because we want an upper bound that is as low as possible. We want to be able to say that the runtime of the algorithm does not grow any faster than a function that already doesn't grow too fast. So in other words, instead of increasing the power of x here, we're interested in decreasing the power of x while still finding an upper bound. So for the next example, we want to prove that f of x is actually upper bounded by x squared, or that it's dominated asymptotically by x squared. So it turns out the proof of this theorem is pretty simple because for any real number without any constraints at all, this number is clearly less than or equal to itself. And this happens to be f of x. This is a constant times x squared. So without any constraints on x being large enough, we just established the upper bound that we need for f of x. So in particular, we match the definition of the big O relationship, where in this case, c is equal to 999, and k is any value we need, really, because this relationship, this inequality, holds for any real number. So let's pick an arbitrary value of k, say 5, and now we have a pair of witnesses that prove this big O relationship. So this concludes our proof that f of x is big O of x squared. Now it's not too surprising because f of x is a function of x squared. Now it doesn't matter how big the constant here is in front because in a big O relationship, remember, we are allowed to multiply the upper bound by any constant. In this case, we just chose the same constant. So for this example, as a conclusion, we see that f of x is big O of x squared. Now, of course, the natural question is whether we can find an even smaller or tighter upper bound on f of x. So to conclude this segment, I want you to think about whether you could prove that f of x is big O of x. So you go down from the second power to the first power of x, and I want you to prove one way or the other that f of x is or is not big O of x.